So trigonometric identities are something that is always true, that has previously been proven so that you can use to replace any sort of situation. It's sort of like the idea that 4 plus 2 is equal to 6, 8 minus 2 is equal to 6, so I can rewrite 6 using any of those combinations. So we have some reciprocal identities. So we've got sine theta is 1 over cosecant theta. We've got cos theta is 1 over secant theta. And then we've got tan theta equals 1 over cotan theta. We have our two quotient identities of tan theta is sine theta over cos theta. And then the reciprocal identity of cotan theta is cos theta over sine theta. And then Pythagorean identities, we have sine squared theta plus cos squared theta equals 1. That is the main one. There are two other ones that you can use. 1 plus tan squared theta equals secant squared theta, and cotan squared theta plus 1 equals cosecant squared theta, but those ones are kind of fancy, and you don't need to know them to do most of the problems. So our steps to prove an identity is always to split it into the left side and the right side. Then we're going to start with the more complex side. Usually you want to change to sine theta and cos theta, and you always want to know where you're going to help you, to guide you in what you are replacing. If you have squares, you might be able to use the Pythagorean identity or difference of squares. You might be able to factor, and you might be able to multiply the conjugate, which is the same expression, but the opposite sign. So the conjugate would be 2x minus 1 for 2x plus 1. So let's look at an example. I can see that my left-hand side is cosecant theta over secant theta. And so I'm going to start with that left-hand side, and I'm going to rewrite both of those expressions in terms of sine and cos. So I know that cosecant theta is 1 over sine theta. And I also know that secant is 1 over cos theta. When I simplify that, I'm dividing by 1 over cos theta, which is the same as multiplying. So that means that when I simplify this, I'm going to get cos theta over sine theta, which is one of my reciprocal identities, which is cotan of theta. So then I can say that it has been proven. I can use QED, or I can use this little box. You only need one of those three to justify that your identity is true. So let's try another one. First thing we're going to do is split it into left side and right side. And then I'm going to write down what I have on the left. So cosecant x over cosecant x minus 1 plus cosecant x over cosecant x plus 1. And then on the right-hand side, we've got 2 secant squared x. And I'm just going to move my line over a little bit so that I have a little bit more space on this more complicated side. So I notice on the left that I've got two terms, and on the right, I only have one term. So I'm going to find a common denominator by multiplying both sides by the other denominator, and I'm going to add them together. So then I've got plus cosecant x. I think I'm still going to run out of space. Cosecant x minus 1. And then my common denominator on the bottom is cosecant x minus 1 times cosecant x plus 1. When I expand out the top, I'm now going to get cosecant squared x plus cosecant x plus cosecant squared x minus cosecant x, which is also a lot. When I expand this on the bottom, I'm going to rewrite this as cosecant squared x minus 1, because I know that this denominator right here is a difference of squares, so it has to expand back to this. On my numerator, I've got cosecant x and minus cosecant x, so those ones cancel out. I'm going to collect like terms, and now I've got 2 cosecant x squared over cosecant squared x minus 1. I'm working towards secant x, so I'm going to change these into 2 over sine squared x, and I'm going to change the bottom to be 1 over sine squared x minus 1. I'm going to go down a little bit more here. So now I've got a triple decker fraction or 4-layer fraction here. Before I do division, I need this to be a common denominator. So I'm going to change this to, I've got 2 over sine squared x all over 1 minus sine squared x with a common denominator of sine squared x. I changed my term of 1 into be sine squared over sine squared. Now I've got 2 over sine squared x divided by 1 minus sine squared x over sine squared x. I know that when I'm dividing, I really need to invert and multiply. So I've got sine squared x on the top over 1 minus sine squared x on the bottom. My sine squared x's cancel out. And I've got 2 over, this is actually cos squared theta, or cos squared x, because in my Pythagorean identity, I know that sine squared x plus cos squared x is equal to 1. So that means cos squared x is 1 minus sine squared x, so I can replace that. And then finally, I know that 1 over cos squared x is actually secant squared x, so I can rewrite this as 2 secant squared x, and if I scroll up to the top, that is what I'm trying to get to, and so I can say that it's been proven. So let's do one more example. This one has tan in it. And I'm going to start the same way. I'm going to split it into my left side and my right side. And I'm going to write down exactly what I have on the left and exactly what I have on the right. Now, I'm really trying to get everything probably into terms of sine and cos. And so in order to do that, I'm going to replace tan with sine x over cos x. And then I'm going to replace cotan x with cos x over sine x. Now I'm going to change 1 into anything. On the top, it becomes cos x over cos x. On the bottom, it becomes sine x over sine x. And I'm going to add the 2 terms in my numerator and the 2 terms in my denominator. So on top, I've got cos x plus sine x all over cos x. On the bottom, I've got sine x plus cos x all over sine x. Now, I've got my triple decker fraction, or 4-layer fraction. And so what I'm going to do, I'm going to really invert and multiply. So that means I'm bringing the denominator of my second fraction up now to the numerator of my second fraction. And my numerator of that bottom fraction goes on the bottom. So now I've got sine x plus cos x on the bottom, which I can simplify. Those are exactly equal. And I'm left with sine x over cos x, which is just tan x. So that's not the right-hand side. So I'm now going to try simplifying the right-hand side. So I got it in terms of tan on the left. So I'm going to try the same thing here. Let's change the bottom, cotan x, into 1 over tan x minus 1. I'm going to add those 2 terms together on the bottom. So I've got 1 minus tan x all over a common denominator of tan x. Then I'm going to pull my division trick. So I've got whatever's in the numerator, and I'm going to multiply by the denominator in the bottom fraction over the numerator on the bottom fraction. This one and this one are exactly the same, so I can cancel them out, which leaves me with tan x. Since both sides are equal to tan x, then it's been proven.